Okay, let's unpack this. We're doing a deep dive into some fascinating research today.
Absolutely. It's from Meta, Google DeepMind, Cornell, NVIDIA. Quite the lineup.
Right, and they're tackling this really core question about large language models. How much do they actually memorize from their training data?
Yeah, it's a huge question because it's not just about, spitting back exact sentences it saw. That can happen, but it's more complex.
Exactly. Is it real memorization, or is the model just, like, really good at guessing based on patterns it learned? That difference is crucial, especially for privacy.
It really is. And figuring out how to measure that specific unintended memorization, the stuff we worry about, has been super tricky.
Until now, maybe. This paper proposes a completely new way to think about it.
They're trying to formally separate that unintended specific memorization from the useful stuff, the generalization.
And our mission today is basically to pull out the key insights for you. Understand capacity, learning, privacy, the whole package.
So first off, defining memorization in these big neural nets, it's not simple.
Right. Like people try to extract training data or use membership inference.
Yeah, trying to see if you can tell if a specific piece of data was in the training set. But those methods have limits.
Like you said, extraction could just be good generalization. It doesn't prove rote memorization.
Exactly. So this paper brings in a new definition. It's based on information theory. Compression, actually.
Compression, how does that work?
The core idea is this. A model has memorized a data point, if you can describe that data point, way more efficiently using fewer bits when you use the model itself as a kind of reference.
Ah, okay. So the model acts like a custom dictionary for that specific piece of data. If the data point compresses really well with the model,
Then the model must already hold a lot of specific information about it. It's memorized.
clever. And this lets them separate things out.
Precisely. They split it into two parts. First, there's unintended memorization. That's the information the model holds specifically about the data set it saw.
That's the privacy worry, right?
That's the one. And then there's generalization. That's the good stuff, what the model learns about the underlying patterns, the data generating process, how language actually works, for example.
And this paper focuses on measuring just the unintended part.
Yes, that's the goal. Independent of how it was trained, just looking at the final model and specific data points, how much extra dataset-specific info is there?
Okay, so how do you measure the absolute limit, like the maximum possible memorization?
Well, this is where they did something really smart. They trained models, GPT-style transformers, but not on text.
Oh, what does they use?
Completely random data, uniform random bit strings.
Random bits. Why?
Think about it. If the data is truly random, there are no underlying patterns. There's nothing to generalize.
Ah, I see. So anything the model learns about that random data has to be pure memorization. It can't be generalization because there's nothing to generalize.
Exactly. It isolates the unintended memorization component. It lets you measure the model's raw storage capacity for that kind of specific information.
Okay, this is getting really interesting. So what did they find? Did models just memorize everything?
Well, they found a very consistent relationship between the model size, the number of parameters it has, and how much of this random data it could actually soak up and remember.
There's a limit then.
Yes. And they came up with a key metric to measure it. Bits per parameter, or BPP.
Bits per parameter. Like how much information is stored in each connection, sort of.
Kind of, yeah. It's the average amount of information about the training data stored per parameter in the model.
And what was the number? The capacity limit?
The headline finding is about 3.6 bits per parameter for these GPT-style models.
3.6 BPP? Is that a lot?
Well, it's consistent. They saw it hover between maybe 3.5 and 4 BPP, depending on the specifics, like the numerical precision they used.
Did using more precise numbers help much? Like using float 32 instead of bfloat 16?
That's another fascinating bit. They tried doubling the precision, which you'd think would give parameters much more storage room.
Yeah, logically.
But the actual measured capacity only nudged up a tiny bit, maybe from 3.51 to 3.83 BPP.
Huh. So most of those extra bits in the higher precision aren't being used for just storing raw training data.
It seems not. It suggests the limit isn't just about the physical space and the parameters, but maybe something about how the information is organized or accessed during training.
Okay, so let's call it roughly 3.6 BPP. That's the ceiling. The model will basically memorize random stuff until it hits that limit, and then it's full.
That's the idea. For random data where there's nothing else to learn, it just fills up its memorization capacity.
All right. Random data gives us the hard limit.
Yeah.
But what about real text? like the fine web dataset they use. Text has structure, patterns.
Exactly. Now generalization comes back into play. The model can learn underlying rules of language, common phrases, etc.
So separating unintended memorization from that useful generalization is key again. How'd they do it with text?
They used a clever comparison technique. They compared the model they were studying, let's call it the target model, to a reference model.
A reference model, what's that?
Usually it's a much larger model, or one trained on a vastly larger data set, representing this sort of ideal general knowledge about the data distribution.
Okay. So how does comparing help?
They define unintended memorization in the target model as the information it knows about a specific training example that the reference model doesn't know. It's the extra idiosyncratic knowledge.
And how do they measure that?
By looking at the prediction error or loss on that specific training data point, if the target model has a significantly lower loss on that point compared to the reference model.
It means it knows something special, something specific about that exact example that the more general reference model missed.
Precisely. That gap and loss quantifies the unintended memorization for that data point.
Got it. So what happens when they apply this measure to models trained on real text?
Okay, so a couple of things. Unintended memorization still goes up as the model gets bigger. Bigger models have more capacity to memorize specifics. No surprise there.
Makes sense.
But, and this is the key difference from random data, the amount of unintended memorization actually decreases as the training data set gets larger relative to the model size.
Wait, it decreases with more data. How?
Well, think about the capacity limit, that 3.6 BPP. If the data set is relatively small, the model can easily memorize a lot of it, maybe even all of it, within its capacity.
Right.
But as the data set gets bigger and bigger, it eventually exceeds the model's memorization capacity. The model can't store all the specific details anymore.
So it's forced to choose.
Exactly. It starts prioritizing. It finds it's more efficient in terms of reducing overall error to learn the general patterns that apply across many examples, rather than memorizing every single unique detail. It substitutes generalization for memorization.
It hits a point where learning the rules is a better use of its limited capacity than remembering every single exception.
That's a great way to put it. It plateaus on unintended memorization once that capacity is effectively full and focuses on generalization.
Wow. And this dynamic, this trade-off, you mentioned it explains something else.
Yes. It provides a really elegant explanation for double descent.
Oh, right. The weird curve where performance gets better, then worse, then better again as models get bigger or see more data.
That exact one, it feels counterintuitive, that middle worst part.
Totally. So how does capacity fit in?
Their finding is that the peak of that curve, the point where performance gets temporarily worse, happens precisely when the size of the data set, measured in information bits, starts to exceed the model's memorization capacity.
No way. So the model gets worse right when it gets overloaded and can't memorize everything anymore.
That's the hypothesis. When data is small relative to capacity, it memorizes. Performance is okay. As data approaches and then exceeds capacity, the model struggles. It tries to memorize but can't fit it all in, leading to worse performance. That's the peak.
But then it gets better again.
Yes, because it's forced to adapt. Since it can't rely on brute force memorization anymore, it has to find the underlying generalized patterns to learn efficiently within its limited capacity. That forced switch to generalization drives the second performance improvement, the second descent.
That actually makes a lot of sense.
Yeah.
The model is forced to become smarter when it runs out of dumb storage space.
Pretty much. It's a really neat connection between capacity and learning dynamics.
Okay, let's pivot to the big one, privacy. This is what most people listening are probably thinking about. How does capacity and this memorization generalization trade-off impact privacy risks?
It connects directly, especially through something called membership inference attacks, or MI attacks.
Remind us what those are.
MI attacks are basically trying to figure out if a specific piece of data, maybe your email, a private message, was part of the data set used to train the model.
A major privacy concern, obviously. So what did the research find about MI attacks in light of this capacity framework?
The results were pretty clear, both for the random data and the real text data. The success of a standard MI attack drops significantly as the training data set gets bigger relative to the model's size.
So bigger data set, harder attack.
Yes. For models trained on truly massive data sets, trying to infer membership for just an average data point becomes really difficult.
And they didn't just observe this, right? They actually built a predictive model for it.
They did. They developed a scaling law. It's a formula using a sigmoidal function shape that predicts how well a standard MI attack will work.
And what does the formula use as input?
It primarily uses the ratio between the model's total memorization capacity, calculated using that 3.6 BPP estimate, and the total information size of the dataset.
And this is specifically for loss-based attacks, the ones that look for that lower prediction error on training examples.
Correct. Those are common MI attacks. The scaling law predicts the expected success rate, often measured by an F1 score.
Did they test if this law actually holds up?
They did. They validated it on the larger models, like different sizes of GPT-2.
And the results? Was the prediction accurate?
Remarkably so. The scaling law's predictions were often within just 1 or 2% of the actual observed MI attack performance.
Wow. Okay, so what's the practical implication here? If you have a huge model trained on a truly massive data set, what does this scaling law tell us about privacy risk?
The big takeaway is this. For the kind of large language models we see today, trained on datasets with extremely high tokens per parameter ratios, think 100 tokens or more for every parameter in the model.
Yeah.
The scaling law predicts that a standard loss-based MI attack trying to identify an average training data point will likely perform no better than random guessing. The F1 score would be around 0.5.
So for the average Joe's data mixed into a trillion tokens, a standard MI attack might just fail.
For an average piece of data based on this loss-based attack method, the risk appears quite low in that very large data regime. That sheer scale seems to provide a kind of statistical camouflage.
Okay, average data seems relatively safe then, statistically speaking.
Yeah.
But that doesn't mean nothing gets memorized, right? Is all data treated equally?
Not at all. That's a crucial distinction. While the average risk might be low, the way memorization happens isn't uniform across all data points.
You mentioned something about a long tail earlier.
Exactly. When they looked at the random data, the amount of memorization per data point followed a nice normal bell curve. Predictable.
Okay.
But for the real text data, the distribution looked very different. It had a long tail. Meaning that while most data points had very low levels of unintended memorization, a small number of points were memorized to a much, much higher degree than the average. They stuck out.
Ah, so some things are just much stickier for the model. What makes a data point end up in that highly memorized long tail?
They found a strong link to the TF-IDF score of the training document.
TF-IDF, refresh your memory.
Sure. Term frequency inverse document frequency. It's basically a statistical measure that reflects how important a word is to a document within a larger collection or corpus.
How does it measure importance?
It looks at how often a word appears in a specific document, term frequency, but balances that against how often it appears across all documents, inverse document frequency. Words that are frequent in one doc but rare overall get a high TF-IDF score.
So, high TF-IDF means the document has unique, rare vocabulary compared to the rest of the dataset.
Precisely. And the research found a strong correlation. Documents with higher overall TF-IDF scores tended to have significantly higher levels of unintended memorization.
Unique documents are easier to memorize, essentially.
It seems that way. They even looked manually at the examples that were most memorized in their experiment.
And what were those like? Any patterns?
Yeah, it was quite revealing. Even though the dataset they used, FineWeb, had been carefully deduplicated to remove exact copies. The examples with the absolute highest memorization scores often contained extremely rare tokens or sequences. And interestingly, many of these were snippets of non-English languages.
Non-English, like what?
Things like Japanese, Chinese, Hebrew, Greek text fragments, even though the model was primarily trained on English.
Wow. So even if the dataset is mostly English, these rare foreign language bits just stood out and got memorized.
It appears so. Those unique sequences act like high TF-IDF features, making them much more likely to be captured in that specific unintended memorization, even within a massive deduplicated dataset.
Okay, this has been a really fascinating deep dive. We've covered a lot.
We've seen this new way to measure memorization using information theory, pinning down that capacity limit around 3.6 bits per parameter for GPT-style models.
Right, a physical constraint. And we saw how hitting that limit seems to explain double descent. It forces models to generalize when they can't just memorize everything.
Exactly. And that capacity limit also helps us predict privacy risks, specifically for membership inference. The scaling law suggests that for average data in huge data sets, standard MI attacks become very difficult.
And this is the crucial, but it's not uniform. There's that long tail.
Yeah.
Specific, unique data points, especially those with rare words or, like you said, non-English snippets, are much more likely to be strongly memorized.
They really are,
Yeah.
even when the overall data set is enormous.
Which leads us with a really important question to ponder, doesn't it?
I think so.
If making data sets massive forces models to generalize better, which is good for performance, and protects average data from some attacks, yet the models still latch on to these very specific, rare, unique examples. What does that mean for truly sensitive or unique information that might accidentally end up in that data ocean?
Yeah, what are the practical safety and privacy implications when that rare data point happens to be something highly personal or confidential? Does the benefit of large-scale training outweigh the risk concentrated in that long tail?
Something for all of us, especially those building and deploying these models, to think very carefully about.